In the current economic and environmental framework, photovoltaic solar energy has emerged as one of the most sustainable and promising renewable energy sources. This project focuses on researching and implementing improvements for this technology, which, despite its high availability and low environmental impact, also presents certain challenges in its implementation. One of these challenges is the variability in irradiance and temperature conditions, which directly affects the extraction of maximum available power, leading to energy waste and reduced system efficiency. Therefore, this project aims to develop a control system that ensures maximum power point tracking, while optimizing the performance of the photovoltaic system. This project integrates power electronics and control systems to propose a solution to the identified problem. The optimization of renewable energy sources is a key concern for sustainable development. Each component and configuration used in the project is thoroughly explained and justified. The project employs both software and hardware tools such as Arduino IDE, Simulink, and MATLAB for its development.
To fully understand the operation of this system, it is essential to explain each of its main components. The first stage is the bus converter, which is responsible for DC-DC transformation to step up the voltage. This is achieved through energy storage components such as the inductor and capacitor, which help increase the current from the power source and generate a higher voltage at the load compared to the input voltage. For this configuration, a microcontroller Arduino is used to control the operation of a fast switching MOSFET, which regulates the system's voltage conversion. The second stage involves the control system, which incorporates an MPPT algorithm along with PID controller to regulate the output current and ensure that the charging voltage does not exceed 24 volts, thus preventing premature battery degradation. A PID controller was chosen from this function as it calculates the difference between the actual value and the desired set point and then adjusts the output accordingly through three mechanisms. One, the proportion control that reacts to the current error. Second, the integral control that addresses the accumulated past errors. And last one, the derivative control that predicts the future errors. By combining these three components, the PID controller efficiently maintains process control and system stability. Additionally, the reference voltage was set at 18 volts as its value allows for maximum power extraction. The output voltage of the solar panel must be higher than the battery voltage, otherwise the output current will approach zero. To ensure the power operation, the maximum power voltage of the solar panel is set approximately in 17 volts, which is determined based on an ambient temperature of 25 degrees. Regarding to MPPT, there are several ways to achieve it, such as Perturb and Observe, incremental conductance method, fractional short circuit current, fractional open circuit voltage, neural works, and fuzzy logic. However, we opted for the first method as it is the simplest to implement.
The input consists of the duty cycle and 24 volts batteries, while for the output, we consider the panel voltage. The ideal duty cycle is determined from the maximum power voltage and the output voltage. Considering the resistive value of the load, the minimum inductance, L-min, and capacitance, C-min, values are calculated for the converter's operation. The switching frequency is 15 kHz and the voltage ripple is set at 0.01. In the worst case scenario, based on laboratory measurements, the solar panel voltage is 7 volts. Therefore, the duty cycle is recalculated as 0.74. With these values, the minimum inductance and capacitance values are determined again. Finally, commercially valuable values were selected for the converter's inductance and capacitance. An 840 microhenry inductor and a 100 microfarad capacitor. our design is based on this switched model. However, it should be clarified the battery capacitance wasn't considered for simplicity. Using MATLAB code, we obtained the operating point and system matrices of the point, allowing us to determine the system average model and the transfer function around the duty cycle. Later, to delve into the control aspect, the controller's transfer function was derived, and using MATLAB's payday tuner tool, we determined the appropriate values for the proportional and integral constant of the controller. With the system fully defined mathematically, a simulation in Simulink was carried out to analyze and verify the designed system performance. Since the objective is to control the solar panel voltage to achieve the maximum power point and supply it to the batteries, the panel's output voltage is measured, and memory blocks are included for the MPPT to compare current and past power variables. This MPPT provides a reference voltage that goes to the payday controller, where the duty cycle of the circuit controlling the bus converter transistor is determined, ultimately obtaining the desired power output. The resulting power, duty cycle, voltage, and current values are shown below. Before implementations, the system limitations were analyzed again, including difference in sampling time between MATLAB and Arduino, battery voltage values exceeding 18 volts due to boost converter configuration, solar radiation variability, and noise in the current sensor.
For this part, we used Arduino due to its affordability, accessibility, and ease of programming. First, the controller was discretized using the testing method, and some modifications were made to the systems simulated in Simulink due to sampling differences, requiring adjustments to control constants, which were determined through trial and error. Additionally, a digital filter, specifically a moving average filter, was added to help control existing noise in the current sensor, preventing erroneous readings or control actions.
After assembling the system and ensuring good solar radiation, the design's performance was tested. Despite minor oscillations, the control was correctly executed, effectively achieving the maximum power point. This successfully addressed the issues of the energy waste and efficiency reduction. For future improvements or application, it is important to consider an overload control mechanism for the battery, which was not implemented due to cost constraints regarding discharge regulators. Likewise, an adaptive control system or an AI-based MPPT algorithm could be developed for greater precision. Our first conclusion was that, in light of the presented analysis, certain limitations were identified related to noise in the current sensor and variability of solar irradiance, and although a solution was implemented for each of them to improve the behavior of the system, an adaptive control or an MPPT algorithm based on artificial intelligence and a battery overload control could be implemented for greater precision. The second one, as has been demonstrated, identifying systems limitations was crucial, as it allowed for improvements providing greater accuracy between the simulation and physical implementation. And the last one, in summary, effective tracking of the maximum power point was achieved using the Perturb and Observe method, implementing a viable, economical, and efficient solution for optimizing photovoltaic systems, contributing to the utilization of renewable energy and reducing energy waste.